everyone. My name is Andrea Manconi. I'm a senior scientist at ETH Zurich and Gamma Remote Sensing since 2019. And today I would like to present you some results of a project. The title is Monitoring Displacements of Complex Landslide Scenarios with Broadband Multiplatform Radar Techniques. This work has been mainly done by myself, my co-authors, Rafael Caduff, Tazio Strozzi, Othmar Frey, Charles Werner, and Horst Wegmuller. A short introduction about the topic. So in the last year, we have seen that radar interferometry has been used more and more to study ground displacement associated with different processes, and also mountain processes like landslides, glaciers, rock glaciers, and permafrost degradation. And this has been, of course, correlated with the increase of the available satellite missions. And we have easier access to data and better spatial and temporal resolutions, and also more than 20 years experience in SAR data processing. So that's the reason why this period is called the golden age of SAR, and we would like to exploit this as much as possible. And for sure, one of the main triggers and drivers of this big shift is the Sentinel-1 Copernicus mission, providing C-band SAR data globally with a very good spatial resolution and also temporal resolution, up to 6 days in Europe and 12 days everywhere. And this has been increasingly used to pass from the standard surveying that before was the case for radar interferometry to a monitoring scenario. And this has allowed also the possibility to generate large-scale regional processes, like what we see here is the example of Norway or Germany, or very recently also an example of what is possible to do at a continental scale, like in Europe. So this is because of the availability of the data and the reliability of the acquisitions over time. Of course, these kind of processings are standard processing, and they are not taking into account the peculiarities of specific regions. So the parameters that you use for the processing are similar for the areas, and you need to match together all the information, and of course you might lose some information at the local scale, although you have a very good global picture of what is occurring on a country or maybe in a continent. In 2018, I've shown here at SGM in Bern a pilot test on Switzerland for a single orbit of the Sentinel-1. In the sending orbit, it was mostly covering almost all the territory without any specific thresholds on the images, so taking all the images available on the Sentinels. We were having some challenges, especially in mountain areas where most of the landslides occur. And the main problems are related to layover and shadowing effects. Of course, the winter images where you have snow cover, and also where you have vegetation that in C-band are causing a lot of problems. You might have some temporal non-linearities that can be maybe missed because of the processing that is mostly generating time series that are associated to more linear processes. And especially when you have large and rapid displacements, this might affect the phase quality and also the results that you might get, so maybe underestimating the real displacements. And in landslides, you have also sometimes complex morphologies and complex kinematic behaviors that are generated by overlapping phenomena. And that's the reason why a standard processing might miss some of the important information that you would like to have to better interpret the landslide. And I show here an example that is a recent example for this project, and also kind of hot topic in Switzerland. So the Brienz-Brienz landslide, which is located in the Canton Graubünden, And you see here is a village that is on top of this slope, that is the Brienz village. And you see a topographic relief which is very steep here, and then relatively flat where the village is located, and also going towards the Albula river. This is a large landslide, and what is called a compound landslide, with different kinematic conditions and different domains that have different geological properties and also kinematic properties. And that's the reason why here is good to have an example of what would be the problem to use a standard processing, and how we can maybe improve the quality of the results we get from radar when we use different approaches. This area is well monitored with different ground-based techniques, and you see here is a bulletin that is released every month from the Albula Gemeinde. And you can see this is one of the latest, in the 9th of October. You have two main areas that are moving with different velocities. So one is called the Rutschendorf, which has velocities up to, at the moment, 1.4 meters per year, or seeing in a different way, 2 centimeters per week. And then the Rutschenberg, which is much faster locally, and you have up to 7 meters per year, or 2 centimeters per day. And you see also the topography is very steep, and you might have also some areas that are covered by vegetation, and in some cases also some snow, you see here on the top. But of course, going towards the winter, you might have snow. So if you would take all the available Sentinel images and generate a classical time series analysis with a PS-like approach or ESPAS approach, you would miss a lot of information. You might get only information in places where you have stable coherence, like buildings. And you see here we have some points in the Brienz village, and all the points that might be related to areas that have a good coherence over time. You have a very good representation for this point in terms of temporal evolution of the deformation, but you miss what is the spatial distribution of the displacement. And it is very important for understanding what is the relationship between, for example, these two domains that have different characteristics, or it's even important to associate the displacement to potential triggers or to potential risk. So this partial view is not sufficient to have a correct interpretation of the phenomena. So the project is building on these main questions, and so it was a collaboration, and was founded by the Canton Graubünden and the Gemeinde Albula in collaboration with a CSD engineer. And so the 4 main points we were investigating were, so we wanted to map the spatial and temporal heterogeneities in the kinematic behavior of the Brienz landslide in the period 2015-2020, which is covered by the Sentinels. Then we wanted to provide some hints on the potential relationship between Rutschenberg and Rutschendorf. Then investigate the potential use of Sentinel-1 for systematic monitoring. You can understand this is one of the issues locally and in this specific scenario. And maybe identify some potential criticalities that with remote sensing you can assess to update the monitoring system that is used for early warning purposes. The methods we use here are based on satellite-based the INSAR analysis, processing Sentinel-1 data, ascending and descending orbit, and doing several interferograms with different temporal baseline, like for example 6 days, 12 days, 18 days, and older and longer temporal baselines. But we also process some ALOS Palsar imagery that is available for the area of interest. It's of course not with the same temporal resolution that we have for the Sentinels, but this is a good information because with a longer wavelength we can maybe get more information in areas that are moving faster and also in areas with vegetation. Then we did also some ground-based radar campaigns by using the Gamma Portable Radar Interferometer, or GPRI, which is a Ku band radar, real aperture radar, and also testing the Gamma L-Band radar in 2 modalities, one rail-based and then car-borne. survey in different metric conditions. So this second part I will not talk too much, because the following presentation from my colleague Othmar Frey will give you more details about the cardboard surveys and also on the instruments. I will show just a few results about that. So you see here the location of the ground-based surveys. We basically had a campaign in in the village, so close by, and all the radar that was already installed there to have a good comparison with these results. And then we also tried to find if it was possible to get good information from the other side of the Albula River and going towards the cantonal road towards the Euler Pass. And you see there are two locations where we tested both the GPRI and also the L-band radar. Here I show you some of the results and the main outcomes. You see here is the results for ascending and descending orbits, just a sample interferogram. And what you can immediately see from these interferograms is that you have there's some strange shapes of the deformation that is not following very well what is the morphology that you have on the ground. And this is mainly caused by different direction of the displacement that we know in this case, but I mean, you can imagine if you apply the similar technique in a place where you have no additional information, it might be quite tricky to interpret. And of course, the combination of the ascending and descending orbits are really important. So one of the main outcome of this analysis was that using just a single orbit might be a partial view on what you would like to interpret in landslides. And another important outcome of the Sentinel-1 analysis is that having such a very good revisit time, so every 6 days, we can even identify specific periods where we have local accelerations that are caused by, for example, rainfall events. Here is an example for an event in October in 2017. You have interferograms that are 6 days apart, and you see that the pattern is changing every 6 days, and in between you had a rainfall event. So the outcome here, so it's possible to identify such a rapid or relatively rapid change when the deformations are still in a certain range. So this is 2017. With the rates we have now in 2020, this would be impossible because the deformation is really large. And just going into this direction, so I want to show you the difference between an interferogram in 2015, and this is a 36 days pair here on the left, and you see the same or very similar pattern also on an interferogram that is just covering 12 days now in 2020. So the deformation, so the surface velocities are nowadays 3 times larger than what we had in 2015. So this is another outcome of this analysis. So here I show some results of the GPRI campaigns. So you see, I don't have to introduce this system. It's already around since several years with a lot of examples and case studies. If you want to have more information, you can see it in our website. So the GPRI is being located here in the location Dorf to monitor the main top part of the Rutschenbriens. And you see we did in this example 2 tests for several hours. And when you have such a very high resolution in terms of acquisitions per minute, you might see also changes over the same day. They might be related to phases that you have, and so this is also important maybe for monitoring. So of course 6 days in such a condition, in such a scenario, is not enough to understand what are especially the local scale kinematics. You see 2 points, and in these areas we know that there are a lot of rock falls with big boulders. You see one that is here down that might be really dangerous for the road that is passing close by. So monitoring with these very high resolutions in space and time is really important. But here you have just a partial view. So we moved also to the other side. So here is a view from a location which is called Ruteira, which is very close to the cantonal road going to the Euler Pass. And you see that here we can have a better view on what is going on the old slope. we see also some transitions between what is the Rutschendorf and the Rutschenberg with different velocities, and we also see this area that is bounded by a dashed line that is behind the crest, and also with some relevant velocities. And this is an important area because it was not monitored with the radar located close to the village. So from this location, it's much easier to monitor. So the two main kinematic domains, which are the Rutschendorf and the Rutschenberg, and also some specific domains that are even beyond the crest. And this is an important outcome of this project. So from the ALOS Palsar L-band data, so we have seen with a few interferograms that depending on the temporal resolution that you have, temporal baseline, you might have high phase decorrelation even with L-band. So in theory, ALOS Palsar can get up to 14 days a repeat pass, but in Europe this is really rare. So here you can see between so pairs of 1 year, 2016, 2017, and 2018 and 19. You can even see some additional phenomena that are occurring close by Brilliance. Some of them they were already known, but you cannot see with shorter wavelengths because they might be under vegetation, and it was impossible to see. Here in 2018, 2019 is already quite strong, the decorrelation. You can bound the area and you see where there is a large movement that is going on. By chance, we got the possibility very recently in 2020 in September to have a pair of 14 days, and you see here is very clear compared to the Sentinel data that is on the right, although you have very good similarities. What is good is that you have an independent sensor with L-band, so longer wavelengths, that are confirming the patterns, the spatial pattern that you see in the Sentinel. So, of course, here in the Sentinel you have much more decorrelation, even in 6 days. But with the L-band, you can get a very good view of what is happening after 14 days. And you see there is almost no deformation recorded in the Rutschendorf, and the reason is this is probably below the detection threshold for L-band, while the upper portion has a much faster displacement. So that's the reason why L-band can be used for monitoring this rapid phenomena, and this is one example of the campaigns with the Carbome radar. As I said, this will be explained much more in the next presentation. See, it's a radar that is mounted on top of the car, and you basically drive and generate this synthetic antenna. And you see here also the rail. From this rail we also use the same radar to get a view on the Rutschenberg. Here's the result with the comparison with the Sentinel-1. So you see here in the figure A just the background of the Rutschenbriens, and here the B is the Sentinel-1 with some of the areas in layover. Of course, with the satellite geometry you cannot see everything, especially when you have very steep slopes. And you can see the transition between areas that are moving and areas that are not moving. And then on the bottom you see the results of L-band with different meteorological conditions. So one in clear conditions, so the C, and the D in during rainfall. So the first acquisition during clear conditions, and then during rainfall after several days, and you still see the information about the displacement, which is really important. So it means with the L-band we could retrieve also information that is very important for the understanding of the landslide. To conclude, so we had these 4 objectives, and so the main conclusions are that Sentinel-1 and ALOS-2 interferograms, they provided a very good overview of the spatial and temporal evolution of the Brilliance. We also are doing now further analysis of the interferograms in cooperation with Canton and also with ETH Zurich, with the group of engineering geology, integrating also information of the subsurface to better investigate the evolution of the landslide, especially the recent evolution, also to help in the characterization and maybe also in the definition of what are the strategies for remediation of the landslide. Regarding the possibility to use 6 days revisit time to monitor and maybe to implement the early warning system, at the current stage we see that the Rothenberg is currently very fast, and it's very difficult to have accurate information also after 6 days. So the C-band interferometry is already beyond the limit that can be used, so in other conditions might be useful, and also in the previous years, but at the moment the C-band is not enough. And so considering the identification of potential criticalities, the measurements we have done from the other side of the Albola River, from the southern part, have shown that we have now a much better location for a radar to monitor all the kinematic domains. And in August 2020, the permanent radar to monitor this area has been relocated, also based on the outcome of this study. A final outlook. So just considering that this regional or country scale processing are now really popular, and I think also in Switzerland there will be soon something in this direction. In some cases, especially for landslide analysis, this may be not sufficient for a correct evaluation of the process. So we need, of course, this large-scale processing. They are really important, but for several conditions we might lose information and maybe not have a correct interpretation. So to have a broadband multiplatform analysis, so combining different interferograms and also having ground-based data, this is well suited for detailed investigation. So the regional scale analysis can be just a first analysis, and then you can focus more and maybe see with different bands and different platforms what are the conditions of the slope. And the outcome of the L-band radar sensors, both the satellite with ALOS with different temporal resolution, so we have seen that this is really going to be probably the future for this phenomena, and there are several missions that are planned in L-band, like the NISR mission or the ROS-L. This is really probably, in my opinion, a game changer also for this relatively rapid surface deformation, because we can really keep the coherence. And we have seen also with the car-based or maybe rail-based or even with other platforms, the L-band can provide a very good solution in such a condition. So thank you very much for your attention, and so here's some acknowledgements, and looking forward to some interaction with you.